The purpose of this video is manyfold. First, I want to illustrate an example of the fact that for an object to not rotate, or to not rotationally accelerate, the sum of torques around its center of mass must be zero. And I also want to blow your mind about how you should really drive when you're approaching speed bumps. Okay, so we have a car here, and it's approaching a speed bump, and here's the center mass of the car. And when you're driving along at a constant velocity, there are two torques applied around the center of mass from the ground. There's a normal force from the front tires that's trying to rotate this car clockwise, and then there's a normal force on the back tires, and we can translate that into a torque which is trying to rotate the car counterclockwise. By the way, here's a good example of finding the moment arm. The moment arm, this value r, is the distance between the axis of rotation, which is the center mass here. Well, it's not really rotating, but it would be the axis of rotation if this car were to start rotating or whatever. So we find the distance from that axis of rotation to the vector that's applying a force that's trying to rotate the car, and that line has to be at a right angle to the force vector. So this would be, this distance here would be the moment arm of the torque applied by the front tire, and then this distance here would be the moment arm of the torque applied by the back tire. And if the car isn't actually going to start spinning around this axis of rotation, this torque has to be of equal and opposite magnitude to this torque. And that example was with a constant velocity. But now, let's pretend you are braking as you're approaching the speed bump. You're slowing down, you're decelerating. And what is happening is that you're hitting the brakes, and there's a force of friction between your tires and the ground that's pushing backwards on the car. And that is causing a torque around the center of mass of the car. And here's the moment arm. And these torques were not here when you're going to constant velocity, because these vectors are force vectors here that are decelerating your car. If it wasn't for these force vectors applied on the ground to your tires, you would not be slowing down as you brake to approach the speed bump. And these force vectors are applying a torque around the center mass, the axis of rotation, and they want to try to rotate your car like this. Flip the back bumper up and push the front bumper down. And you can kind of feel that happening very momentarily. As you brake, you can kind of notice that the front of your car goes down and the back goes up a little bit. But as soon as that starts to happen, as soon as the front goes down a little bit, the force applied between the tire and the ground increases. So there's a lot of force, a lot of normal force on the ground applied to the tire in the front to create a torque that wants to rotate the car back in the opposite direction. And as the back of the car lifts up a little bit, the force decreases. So if you did have a force like this, now you have a force maybe like this. So there's actually, if you were to put a scale under the back tires, that scale would read less as you're braking, and if you put the scale in front of the front tires, it would read more as you're braking. But the end result is that the sum of all of these torques, the clockwise torque here, and the two counterclockwise torques here, and this counterclockwise torque, if you add them all up, it's equal to zero, because, well, in the case that your car isn't actually flipping around in either one of these directions, if you add up all these torques, it should be zero. So these three effectively cancel this one. Or you could say that this one cancels these three. Whatever. But the point is, do you really want to approach a speed bump when there's a lot of force between your front tire and the ground? No, because when you do hit the speed bump, there's going to be a lot more force, and it's going to jolt your car more, and I don't know, maybe damage your internal components, who knows. So counterintuitively, you don't want to be braking at the moment that you hit the speed bump. Here's how a better way maybe to approach a speed bump. You see it coming and you slow down a bit, but then right before you hit the gas and you accelerate your car. In that case, let's assume you have rear-wheel drive here. The ground applies a force to your tire to accelerate it forwards, like such. And that creates a torque that wants to rotate clockwise around your center of mass of the car. And that means that for your car to not start rotationally accelerating and flip end over end, your torque applied from the ground to the front tire has to decrease a little bit. And at the same time, there's a little bit bigger torque applied from the ground to the back tire to try to counteract it. This torque wants to rotate counterclockwise around the center mass, and that counteracts the clockwise torque from the frictional force between the tires and the ground that wants to cause a clockwise torque. And in this case, when you hit the speed bump, there's less force between the ground and the tire, so it's less jarring of an impact when you do hit the speed bump. And this again was a case where you're actually accelerating or hitting the gas pedal the instant before you hit the speed bump. But do remember, you should take your foot off of the gas pedal as soon as your front tires have crossed over, because if you're still accelerating when your back tires hit, there's a lot of force there. So you should hit the gas the instant before your front tires hit, and then take your foot off the gas, or even hit the brake a little bit before your back tires hit. Try this out in real life, see if you can notice a difference. But do remember to slow down before you get really close to the speed bump.